Eventually today's presentation will be on cover meter and the correct use and theory of pulsed eddy current cover meters in particular. I just want to begin by pointing out a few new products available from PCTE. We have on our construction instrumentation side a new bulk temperature and concrete maturity and strength measurement system, RPX Insight. We've already supplied many of these and we're very pleased with them. They take the best of a wireless temperature probe system and a wired temperature probe system for a really bulletproof system way of recording the temperature in bulk concrete pours. And there's also the ability to use this as a concrete maturity system. So to evaluate early age strength gain based upon the temperature of the concrete in situ. On our industrial NDT or our metal NDT side, we are now working with Doppler as a supplier for ultrasonic floor detection instruments, phased array instruments, and a variety of ultrasonic probes. We also are currently taking part in an X demonstration equipment sale. The website's been updated with all the information on some ground penetrating radar equipment, some borescope, videoscope systems, and more to have a look at if you'd like to take advantage of our secondhand equipment sale. So let's go on to our main discussion for today, which is going to be about cover meters. During this presentation, I'm going to try to make sure that people who've attended can tell when a pulsed eddy current cover meter is the most appropriate choice and how that relates to other systems such as ground penetrating radar and ultrasonic testing. I will discuss the theory and the different precisions this gives us in the measurement of cover depth, rebar sizing, and rebar position. And also how you go about choosing a cover meter based upon the structural elements expected in an area and what to do when it's an unknown area. Finally, I will talk about a procedure and the specific operation of Prosex, Profiscope, and Profimeter cover meters, which are sort of the basis of some of the content today. But the basic procedure should be applicable to all cover meters, but we've been working with Prosex for a long time now and are very pleased with the Profiscope and Profimeter cover meters. So let's just, before we dive into the what and how, let's just quickly look at the why. The thickness of concrete above reinforcing steel in a structure exposed to the outside world is one of the biggest controlling factors of the design life and expected service life of that structure. Cover deficits have real costs because they allow issues such as expansive corrosion of reinforcing steel in marine environments to occur earlier and reduce the time to first damage of that structure. So even as much as a 5 millimeter cover depth deficit from the expected cover can take more than 10 years off a 50-year design life. So it's really important to get the cover right. This is why you will see projects have fairly precise cover specifications and the use of non-destructive tools to confirm that cover is achieved. The particular non-destructive tool I'm discussing today is an eddy current cover meter. To compare that to ground penetrating radar systems and various forms of ultrasonic pulse echo tomography, which is another imaging tool, there's different sensitivities, different precisions, and different sort of depths of focus. The cover meter, eddy current cover meter, is the most shallow depth. A normal cover meter is going to have an approximate absolute maximum range of around 140 millimeters to 200 millimeters, depending upon how large the reinforcing steel is. And it's going to be somewhat thinner than that, at which the cover meter can actually locate individual reinforcing steel. It may still be able to determine the cover depth correctly, but there's there's points where it can no longer isolate steel bars. Ground penetrating radar is probably most similar in sensitivity. It is also sensitive to reinforcing steel and most sensitive to other forms of metal as well, post-tensioning tendons, other forms of embedded steel, and has a weaker sensitivity to other embedded objects such as conduits, plumbing, cables, and other areas. Cover meters, meanwhile, are absolutely limited to use over reinforcing steel. They're sensitive to other metals because the eddy current process is sensitive to metals, but when you're planning your cover survey, you need to consider other forms of metal, things that are not reinforcing steel, as a source of interference rather than as something you can locate and measure with your cover meter. It's not the right tool for that. A ground penetrating radar would be more appropriate. On the other side of things, ultrasonic pulse echo tomography, like ProSix Pundit's live array, is very sensitive to air voiding. So it's somewhat better for finding conduits. It's very good for finding delamination and reinforcing steel in structures. But it's only got a weak sensitivity to metal, including reinforcing steel. I have occasionally had projects where ultrasonic tools are used to evaluate cover depth, but that was only because every other technique could not work, specifically in steel fiber reinforced structures. There is no way to use a ground penetrating radar scanner or an eddy current cover meter on a steel reinforced fiber structure. So we'll continue on talking about eddy current, and we'll begin with physics and a little bit of the limitations and precision of the cover meters. Now, if you do have questions as we go along, please drop them in the chat box, or let me know by turning on your microphone. I'm happy to discuss anything as we go through here. The basic principle of an eddy current cover meter is we have an alternating current in magnetic coils, and we bring those magnetic coils close to the reinforcing steel. We then measure the signal strength of an induced current in that reinforcing steel. That signal strength is affected by the distance of the steel and the size, the diameter of the steel. Any forms of metal inside the magnetic field will increase the signal strength, but the way cover meters are designed is they are assuming a single reinforcing bar is within that electromagnetic field aligned with the electromagnetic coils. So when you have, say, a 90-degree crossing of reinforcing steel in the other direction, that would artificially reduce the cover depth. We want to avoid measuring over areas like that. And similarly, if we have scrap metal or other elements within that electromagnetic field, they will also be a source of interference. Now, pulsed eddy current is the most recent development of cover meter measurements. Previously, they used a magnetic induction, which maybe had a little bit more depth, but was much more interfered with, would have a lot more drift over time. So unless you specifically know you've got a ferromagnetic cover meter, most cover meters today are pulsed eddy current. So let's go a little bit more into exactly the measurement procedure. We begin by transmitting from one electromagnetic coil an alternating current, which produces an electromagnetic field around that coil. This induces in the reinforcing steel a matching current and a corresponding electromagnetic field. By allowing the first field to decay, it can then sense the strength of that electromagnetic field with a receiving coil. Now, cover meters typically have more than two coils. The simpler, older style units could only read this signal strength, whereas the Profiscope can actually locate reinforcing steel by balancing signal strengths. And the Profimeter has some multiple coils, which make it very easy to align it in the clearest possible space for the most precise cover depth measurement. So this is the basic principle behind eddy current cover meters. We're producing an electromagnetic field and we're measuring the strength of the response. Based upon the strength of that response, we take that to have a direct relationship to the depth of the reinforcing steel. So looking specifically at the Profimeter probe, there's two match pairs of transmitting and receiving coils. And they can do some clever things. And this is where the first part of the measurement procedure comes in. When you have a cover meter with multiple measurement ranges, so a Profimeter has a standard range and a large range and a spot range, and a Profiscope has a standard or a large range, you want to choose the lowest intensity of system so that you don't so that you're less affected by anything in the area. So the standard range is the standard choice for the Profimeter, and the Profiscope, the short range. In both of these cases, the electromagnetic field is smaller. You'll find that the depth is limited to around 80 millimeters for 60 mil reinforcing steel, but that prevents, say, a second layer of steel in a multiple-layer reinforced, a dual reinforced slab or floor from having as much effect on the measurement. It also means that other forms of interference need to be closer to affect it. If we change to the large range, we're going to expand out to our maximum depth range, so around that 180 to 200 millimeters maximum depth, but it's going to be more easily interfered with. On the Profimeter 2, we have a spot probe range that uses only one of the two electromagnetic coils. That's not typically used except to get into tight corners and areas like that. So just to show you the difference in these different coils, this is the standard measurement range. So this is the one we would operate in normally. If we then have a look at the large range, you can see that the electromagnetic field has a much larger region of influence, so it's more easily interfered with by closely spaced reinforcing bars. And finally, the spot range only uses one of the electromagnetic coils. Again, that's intended to get into tight spaces. Now, the second thing to consider is the effect that our two controlling factors have on the signal strengths. We have the distance of the rebar to the cover meter, and we have the size of that rebar, the diameter. If we have a reinforcing steel bar, say 60 millimeters, moving closer and further away from that coil, it produces a large change in the signal strength to that coil. Because this change is large, it means we can get a very precise variation, even if we move that cover meter only a couple of millimeters higher or lower. That's why when we talk about cover depth, the cover meters, we consider that to be a measurement, and we give it an error range, typically 1 or 2 millimeters within normal cover ranges, maybe 3 to 4 at the extreme ranges of the cover meter. Very precise, particularly when the correct reinforcing diameter is entered into the cover meter. But if we instead look at a change in rebar diameter, so say from going from a 12 mil bar to a 16 mil bar, keeping the cover meter at the same depth, the change is small, quite small, which means that it's not very easy to distinguish smaller bars from larger bars. And it means when I talk about the diameter measurement functions of a cover meter, I'm going to call those an estimate, and I'm not going to give an error range. It's not, while it is the only tool that I'm aware of, and I believe in the market, that can estimate the size of the reinforcing steel, except maybe barring X-ray measurements, it is not the most precise tool for that. And it's typical to confirm if rebar size is very important, to confirm with destructive measurements as well. So we do have that sense. So there's a sensitivity there, and we've just had so from Ray Valdez, we had, what do we do when the rebar diameter is not known? That's a good question. And I'll talk about that when I look at some of our precisions, but it's common to assume a value and to understand when we make that assumption, what that's going to do to the precision of our measurement. And also to use knowledge of how the structure may be built to select a reasonable value. So 60 mil bars in conventionally reinforced structures, understanding that something like a slab on ground may only have a sort of thin welded mesh, which we can set to 12 millimeters, but that welded mesh is actually going to also be a more difficult measurement to make. It does have an effect on the expected size. it does have an effect on the cover depth as well when you weld a mesh rather than tie it together. It turns a little more signal strength to the cover meter. So let's go through a few limitations now. This is very important with any tool that you do look at. You're going to only have a maximum range, 152, 200 mils, depending upon the size of the bar. A really important one is lapped reinforcing bars. Lapped reinforcing steel, by which I mean when you have one bar laid close to another, when it's been essentially forming a join between two separate sections of reinforcing steel. That can be detected as a single bar location-wise, but it's going to give a very thin cover compared to an isolated single bar. You can commonly see this when you're doing a larger scale cover survey and you measure the reinforcing steel depth. There will be regions periodically spaced, maybe 1.5 meters from each other, where the cover appears a lot thinner, and that would be the region where reinforcing steel is lapped. I've got some diagrams later where I can explain that in a little more detail. Now, we do want to make sure we isolate our measurements from other bars traveling perpendicular to the bar we're measuring to. Again, I'll have some diagrams. I'll talk about how to do that. But if we want the most precise cover depth measurement, we want to have a single bar isolated as much as possible from any other steel nearby. Typically around 15 centimeters, 150 millimeters is what we deem to be the range of the electromagnetic field. So we can get everything else outside that range. It's like measuring a single bar by itself. If we can't, there are factors like neighboring bar correction that are going to be an effective tool to correct for the interference of closely spaced bars, but we need to know to use them. So we need to this is why we need to understand the structure before we take our final cover depth measurements. Now we're coming to accuracy now, and this is where I want to discuss a bit about what we do when we don't know the rebar diameter. So what cover meters essentially do to get cover depth is they have an internal table of signal strength to cover depth, and the third factor on that internal table is going to be correctly entering the size of the reinforcing steel. The precision of the measurements is defined in these charts here. So we're typically looking at 1 millimeters to around 40 to 60 mils depth, a precision of 2 millimeters out to around 100 mils of depth, and then 3 or 4 millimeters out to the maximum range of the cover meter, assuming we've entered the correct reinforcing steel. Now, the diameter estimates have a shorter range. You're typically only going to successfully estimate a diameter to about the 50 millimeter depth. It's about 80% of the short range because the actual measurements use both the short and long range for diameter estimates. So this example is where we can look at what happens if we don't know. So this chart, reading it here, we have a flat line for 60 millimeter diameter. So no additional uncertainty. So no additional millimeters of cover that would appear by having the wrong setting. Then we see the effects of choosing a 12, 8, or 6 millimeter bar rather than the correct 60 mil, and also 20 down to 40 mils. A couple of things to see from this chart. The short range has less variation than the getting beyond that 40 millimeter section where the uncertainty increases more sharply. The way we can use this is, let's say we don't know the reinforcing steel, but we assume it's going to have a size, say between a 20 millimeter bar to an 8 millimeter bar, which I've marked with a red line here. So by marking with that red line, I've defined the errors that I can expect in each way. So with a cover measurement of 60 millimeters, we might have 2 to 3 millimeters underestimate and as much as a 15 millimeter overestimate of the reinforcing steel depth. These charts are available in the cover meters manuals. This is one way when you're producing reports where precision is important to let your clients know, here's the additional uncertainty we're taking into account because we weren't able to investigate and determine the real reinforcing steel size. Now, it is possible, and again, recommended when you've got critical cover surveys to combine them with some destructive investigation. So you can confirm the size of the reinforcing steel bars, and you can also confirm the actual real cover depth with physical measurements and make any final tweaks to your settings to get the very best cover depth measurements possible. It's not always possible, but it's helpful. Another correction you can do is if you only have a cover meter, but you also are a ground penetrating radar surveyor, is you could get the best depth measurement you can with a cover meter and use that to set up your total, set up your ground penetrating radar dielectric constant or thickness adjustments to correctly report based upon that cover meter measurement. That will still be more precise than a radar measurement would be. So let's look at some diameter estimates. The basic procedure for rebar diameter estimates is the system will determine the signal strength with a setting of short and long range energy. And it will then, again, look up what that would indicate the bar size to be. It is an estimate. I don't want to give a particular size in plus or minus ratio, but you would really want to confirm this if it was a critical measurement. If you're doing an investigation for a structural engineer and they have to know the bar sizes for their calculations, this should be confirmed destructively. So do we have any questions before I go on to looking at the procedures for measuring cover based upon what we discussed about theory and the practical elements of measurement? You're quite welcome to unmute as well if you'd like to. Okay, I'll keep on moving. Thank you. So in the procedure, the first thing to consider is we want to look at what are we actually trying to determine. So in some cases, it might be a QA assessment where what we need to know is, have we achieved the minimum cover value over the entire structure? Or is the average cover equal to the expected cover value? It's also appropriate in simple cases to use cover meters as a bar location tool. You don't want to do that if you are cutting so much because it's not sensitive to other dangerous targets like conduits. And it's definitely not the right tool to locate post-tensioning strands or pre-tension cables. But in simple cases where locating reinforcing steel is needed, cover meters can be used within their working range. If you're going to take bar diameter estimates, you need to define that you'll be doing that. And sometimes you need to produce data logging results, and other times you simply need to find good or bad regions. So this is all going to control how you go about that process. Now, let's look at a few case studies of how you may pick a system, cover meter or otherwise, to evaluate the cover depth. So start with the simplest one and jump on the microphone if you'd like to respond or put a note into the chat. If you have a minimum cover of 40 millimeters, so your requirement is you must have 40 millimeters or greater cover depth, and you're measuring with a slab on ground, what would you need to take out to do that? Would a simple eddy current cover meter be appropriate? Would you need any data logging functionality, or would another tool be more appropriate? I'll have a look on the chat, or again, please feel free to unmute if you like. All right, so look, this is probably just a Profiscope and a notepad and a tape measure we've got from Nat Cox. From Ray, we have rebar diameter and normal cover meter, and that's quite right, Ray. If we were building this, we'd know the diameter, so we'd be able to choose that correctly. If it was a welded mesh, we may actually want to get a piece of the mesh and do a few experiments to choose the right settings. We've got a question from Niraj, which is about, is it not possible to use a cover meter to detect post-tension strands at all? So the cover meter is definitely sensitive to the metal in the strands, but the way strands move through a structure make it less appropriate to detect their presence with the cover meter. So if it's post-tensioning strands, they're going to have varied depths. They'll be quite close to the bottom of the structure. So to the bottom of the slab, if it's a suspended slab and it's over a span, and it'll be quite close to the surface near to columns and beams, by the way post-tensioning is designed. So it can be quite a bit below the maximum depth of the cover meter in a lot of the structure. It's also a lot of reinforcing steel. So the cover depth measurements are going to be well out, so the signal strengths are going to be well outside the normal expected diameters of that strand. So it's just not the right tool. It's sensitive to the steel. So if it's close to the surface and you pass a cover meter over it, yes, it will respond. But if we want an accurate depth and an accurate position over most of the structure, like we normally do when we want to detect post-tension or pre-tension strand, it's better to use something like a ground penetrating radar, which has a much larger working depth with the prosec ranges as much as 500 to 700 millimeters maximum depth compared to the cover meters 150 to 200 mils maximum depth. And it's also much more visual, much more able to help the operator see the whole picture of that structure, because when you're determining the position of post-tension strands, you're doing it in structures that also have reinforcing steel, also may have other embedded objects like conduits, cabling, plumbing, and more. So the visual presentation of that radar makes it more able to do that job. So typically when I'm talking about post-tensioning, I almost talk about it as a form of interference to a cover meter, something that makes it hard to take a good cover depth measurement to the reinforcing steel. Radar would be more appropriate. So our second case study, we have a bridge girder with 100 millimeters bar spacing, anti-burst cages, by which I mean additional reinforcing close to edges where force may be applied, and a minimum 40 millimeters cover. So it's fairly similar to the previous example where we've got a minimum cover we need to achieve. But now we've got a more complex layout. Now we have another question, which is, would you need to know if the mesh was welded or tied to allow for error factor? It is very helpful to know if the mesh is welded or tied. As I said, welded mesh can return a stronger signal to the cover meter. It also tends to really overestimate diameters of welded meshes as opposed to tied reinforcing mesh. It's somewhat common to consider larger reinforcing steel to be tied and thin reinforcing steel to be welded, just because of how it's typically brought onto site. But the more you know, the more precise you can be with the tool. And this is where, if you don't know and you've got a really critical measurement to take, you do need to start considering whether the structural investigation needs to be part of the project as well. So in the example I was giving about a more complex minimum cover process, it's absolutely appropriate to use a simple cover meter. If we know we have 100 millimeters bar spacing, we should use some form of neighboring correction factor, or another way of eliminating the influence of those closely spaced bars. So continuing to the next example on just selecting the right tool for the job, an unknown residential floor, which is of a suspended slab. So in this case, we have many of those questions we were just talking about. If we can determine that it's a post-tension construction or just a conventionally reinforced construction ahead of time, it's more easy to choose the tool. We do need to be very aware of regions that might appear to have very thin covers being due to additional reinforcing steel near the cover meter. And it may be appropriate, particularly if we want to know how that floor is constructed, to use a tool like ground penetrating radar in preference of a tool like a cover meter. Now, we have another example, scan before drilling through a tilt-up panel, which is maybe one case where a cover meter could be used, because it's very unlikely there's anything in that panel except reinforcing steel. Whereas once we get to something like a scan before drilling of a suspended slab, that is absolutely not appropriate to do with a cover meter. It's not sensitive to everything that may be embedded in that slab. It doesn't have the depth to determine targets the whole depth of the slab. It's just not the right tool. Another example is a dilapidation survey, where information about cover depth can be quite valuable to determine is the structure at risk of corrosion. If you've got very thin cover in regions exposed to the outside world, that's an important input into the long-term life of that structure, particularly if you're taking other information like chloride depths or carbonation depths, which you can compare to the measured cover depths of a structure. And that's similar with inspection before the remediation of a bridge structure. It's very important to understand what the cover's doing, and is it still providing protection, or is it too thin and the outside world is starting to cause troubles on a structure that's going to be remediated. That's a few examples just about choosing the tool for the job and how tools are used. Do we have any more questions from that before I move on? Again, feel free to unmute or just drop a question in the chat box. All right, thank you very much. I'll keep going. So let's go to the main point of today's presentation, which is how to operate the cover meter to measure cover most precisely. And it all comes down to understanding as much as possible how the structure is built before you take your meaningful measurements. So on a simple reinforcing steel layout, you're going to want to mark up the position of the reinforcing steel. I've put these marks in red to indicate that we are not yet recording and saving cover depth measurements. We're only using that cover meter to determine the position of the reinforcing steel bars. We also want to determine which reinforcing steel is closest to us, because that's the most important for the cover depth. So once we've determined the position of the steel closest to us, the thinnest cover, we can then move our cover meter probe through the middle of the perpendicular bars and begin to mark positions and record cover depth measurements. Once we've got that, we can then take our most critical cover depth measurements, where we're recording the depth of the reinforcing steel closest to us, with measurements right through the middle of any perpendicular bars. So if you just take the cover meter and place it on the surface, you're not taking these steps to remove the influence of additional reinforcing steel. So coming back to our limitations, when we have a single reinforcing steel bar by itself, or bars that have a separation of around 150 millimeters or more from each other, that's entirely appropriate to measure to with no adjustment. Once reinforcing steel is closer than 150 millimeters from the neighboring bars, a correction factor should be used. And regions where you have lapped reinforcing or having the probe oriented on top of perpendicular bars, you're not going to be able to take a precise cover depth measurement in those areas. So if you're setting up something like a data logging functionality, you still need to know, at least in general terms, where lapped regions may be, or be willing to say that this region halfway down our data logging measurement area is indicative of lap reinforcing steel, and we should consider the areas above and below it as our correct cover depth measurements. So we've talked about the simple elements. We've talked about how to go about getting the best places to measure. So what about some of the complexities of the matter? Even for simple slab on ground, we still need to consider that the orientation is as we expect it, that we know that the diameter we've entered is a reasonable choice, either based upon our knowledge of structures or our understanding of what's there. And we also need to take into account any bar spacings. Once we go to a more complex layout, this is where it's important to come armed with enough information to do the survey. If you have access to drawings, this can help you choose regions that are clear to survey. If you have to measure cover in areas with dense reinforcing steel, it's important you use a cover meter, which can be set up to do a QA assessment of good and bad, or to understand what to do when the steel is so dense. Your cover depths are not going to necessarily correspond with normal diameter settings to the real cover depth. So firstly, a question for everyone here: what regions on this rebar layout are going to be appropriate to survey with no modification of the cover meter settings? Just sort of, say top left or middle right, or just give me some positions in the chat, or you can unmute if you'd like to. Top left area, which is correct. That's just more like a conventional reinforcing setup, so there's no difficulty measuring in that area. Has anyone spotted any other points in there that would be appropriate? Dennis has none. I'm interested to see why you're saying none there, because it might be a logic I'm not using, which would be good for everyone to keep in mind. Dave sees top left or top right, which again, that's a reasonable space. Ray's got a little more nuance with top left if we hit the rebar spacing is 150. Dennis Brown is indicating that it might be welded mesh. Which again is a reasonable consideration. If we had the drawings or we knew how it was constructed, we'd know that. So again, if we assume we don't have a welded mesh situation, we are able to, without correction, to survey top left and top right. There's also a couple of spots here and here where we can isolate an individual bar, but we'd have to know those spaces were clear to measure, and we couldn't do it just by sketching the layout on the surface. Another region here would be appropriate because it's unlapped, but you would need to use something like a neighboring rebar correction. So again, this is not a perfect example. It's just something I've sketched up just to show the way that you need to go about thinking to determine regions that are appropriate to do cover surveys. For example, if you did need to determine that the lapped regions had sufficient cover, it may be appropriate to make a mock-up and then measure with a plastic ruler what signal response would occur near to that mock-up and use that as your criteria. Maybe adjust the bar diameter to better represent that lap situation. And Profimeter cover meters actually have several correction functions that are intended for that procedure. So if you have a precast yard and you have your cages visible, you can pick spots that you'll be doing QA measurements on and record a calibration setup that will measure depth for QA purposes correctly to those ones. So that can be quite helpful when you're using a cover meter for QA. The Profimeter's a very powerful tool for more complex jobs. So just a few examples on interference. Is the second layer of rebar, so top and bottom steel, going to be a source of interference in a 250 millimeter diameter thick slab, given what we understand of settings and cover meters? And again, so if you drop some answers in, please. Okay, and yeah, it's reasonable to consider that in a standard measurement mode, we're not going to have any substantial interference from that. If we do go on to a dual layer reinforcing in a 150 millimeter thick slab, it's going to be more difficult, because with 150 millimeters, it's quite likely, even with the short range, the electromagnetic field is going to be somewhat influenced by the second layer of reinforcing steel. And yes, absolutely, it does depend where the second layer is, and the more information we have, the more we're able to balance this. So is a post-tensioning tendon would be a source of interference if it's within the electromagnetic field of a cover meter. Tie wire, dropped to the bottom of the formwork, I haven't seen any influence of this sort of thing from the top, but when I've moved a data logging cover meter over the bottom of a slab, there's a couple of regions where there's just a few pieces of tie wire that indicated incredibly thin cover because that tie wire was so close to the surface of the probe. It doesn't need to be a lot of metal to have a strong influence if it's close to the surface of the cover meter probes. Power cables, because it's an eddy current cover meter, it is responsive to metals, not just steel. So that will have an effect. Yeah, if you did have a steel bar chair, you would certainly have that have some influence on the measurements, particularly if you were measuring from the side with the bar chairs coming in. Now, iron oxide aggregates like that have less of an effect on an eddy current. You're not really considered that a colored concrete would be difficult to measure to. Now, and if you did have stainless steel, because the cover meters are eddy current based, they will respond to the stainless steel. It's definitely worth confirming that the measurement is the same to a mild steel reinforcing, but there is definitely response. Now, cast in place formworks, say like a bond deck, because those slabs can be quite thin and there's a lot of metal down the bottom, it could be a source of interference. Now, it's not that stainless steel will necessarily give less response. It's just worth confirming it gives the same response because it's not the same material exactly. So it's always worth double checking if something differs from the assumed case. And the assumed case is conventional reinforcing isolated. And the commentary on ferritic or duplex stainless, I simply haven't tried enough different forms of stainless to know exactly the response of every piece. It's certainly the case where, because it's an eddy current measurement, if it can conduct the electrical currents, then it should produce a matching electromagnetic field. If the steel electrically cannot produce a matching electromagnetic field, it wouldn't be detected by the cover meter. So just a few looks at some of the actual systems that get commonly used. The Profiscope cover meter is a more simple cover meter device. It's got the same precision as a larger two-part cover meter with a probe and separate readouts. So you don't necessarily choose a Profiscope because it's smaller and less precise. It has the same precision, but it's a simpler device. So doing the most complex work is going to be difficult. It's also reasonably limited in data logging. So just to show the operation, this is me with my old hair. But we can see here that the cover meter is sensitive to reinforcing steel before it's reached and will lock on. I've placed my measurement point, which is the crosshair near my thumb, towards the middle of the reinforcing steel bars, and I'm moving that over. And when the circle approaches the opposite direction I'm moving the probe, we can lock onto individual bars. And I can move, I can also detect the midpoint when the circle is moving in the same direction as I'm sliding that cover meter left or right. Again, locked on. I've entered a 60mm diameter bar, which is, this means this will be our most correct diameter measurement, because the bar on the right is smaller, the bar on the left is bigger. We see that maybe that diameter estimate was perhaps not as good as we would like. So again, good for depth, not quite as good for diameter. Now the Profimeter cover meters, compared to the Profiscope, these are better for presenting results and better for complex work. So we have an analogous operation mode to the Profiscope where we can line up the cover meter over top of a bar and record values of cover depth and diameter estimates. But where it differs is we're going to be able to see better how our probe is aligned. So on the right-hand side, we can see a couple of examples. When we are correctly balanced between top and bottom perpendicular bars, we have an indicator showing us that's happened. If we are moving over bars that are not aligned parallel to the cover meter, the machine can indicate that. And in this case, I've placed the cover meter so a perpendicular bar is directly underneath the lower coil. The signal response is uneven, and the machine actually tells us, don't measure here, don't measure here, measure in the balanced clear region. So it's already helping the operator make intelligent choices about the right place to measure cover depth from, more so than the Profiscope does. Which means that while we should certainly still be marking the reinforcing positions on the surface of the element before we take our cover depth measurements, the machine's helping us get it right, even if we've been a little bit careless while doing that. We now go to some of the data logging functionality. This is my favorite mode to operate a Profimeter because we still have the same response to show us what we're doing, but we also now have a cross-section similar in rough layout to how a ground penetrating radar measurement would be, but again, only addressing a single layer of reinforcing steel. The yellow line is signal strength or cover. So the top of that is the position of the reinforcing steel bars, and it's possible to individually enter or take diameter estimates of the bar sizes, and that can show why some have slightly different depths than others. So it's possible to set this up to provide quite a precise report of cover depth by spacing in one direction. There are also multiple line measurement modes. So this is more like looking top down and determining depth of reinforcing steel this way. So in this example, it can be seen that the cover depth is shallower on the left-hand side of the survey and deeper on the right-hand side. So again, this is all ways to present data clearly with the same eddy current measurement of a cover meter. Now, finally, this is an area scan mode. It's minimum cover within each region is what's presented here. And this is particularly intended to combine with half cell potential measurements, which is an evaluation commonly used for durability. So just highlighting some of the ways to present data available with the Profimeter. That's the conclusion today for just a discussion about correct use of a cover meter, things to be aware of while operating them. Does anyone have any more questions, any comments they'd like to make from their own experience using cover meters? I'm happy to chat a little bit before I sign off for the afternoon, and thanks so much for joining me today. I'll keep an eye on the chat, or you're quite welcome to unmute your node as well.
William, Albert here.
How's it going, Albert?
Good, thank you. Sorry, I've been trying to send a chat. I can't get it through somehow, but my question...
that's no problem at all.
And once again, excellent presentation. My question is the results for saturated versus dry concrete. Is there a difference there?
Water's going to have a very... Essentially, you could use a cover meter underwater. They're not affected by the same way that something like a ground penetrating radar would be. Because they're it's physically inducing electromagnetic fields moving through steel. If there is an effect, it's a very limited one.
So GP, ground penetrating radar, would be much more effective, you're saying?
No, ground penetrating radar is actually very affected by the moisture content of your concrete.
Yeah.
So if you have a lot of moisture, it can actually make it very difficult to use a radar. Cover meters are a lot less affected by moisture content.
Okay, thank you.
Thanks, William.
Oh, no problem. Is there much of an impact if there are anodes installed? Now, that's an interesting question. I haven't seen much work done over regions where the anodes are already in there. They are metallic. They will definitely act as a source of interference. So if you are measuring that area, it's certainly going to have an effect. Usually, of course, the cover meters are brought in before the anodes go in to see that the areas are clear. And they work quite well for that. There's also specialist ones used to pass down holes, which are separate to other cover meters. So yes, Dave pointed out it's very important to recognize the measurement point for a Profiscope, and that's quite correct. Every cover meter has a center point where it's deemed the measurement occurs, you need to know where that is before you move it over and take cover depths, because otherwise you can be misaligned if you just use the visual center of the probe. A question from Matthew about how does steel fiber affect readings? Did you say it becomes impossible? That's right. If you have steel fiber reinforcing, essentially the metal's right on the face of the probe, it's going to stop there. So it's not going to work. Ground penetrating radar also won't work. The only thing that has any chance is ultrasonic measurements, and they're quite difficult to use. I've seen it done once or twice, but it's not a common tool. So again, you're quite welcome to, again, if you've got feedback, questions, or personal experience, now's a great time to speak up or do anything more before we sign off for the day.
Hi, William. It's Nat here.
Hi, Nat.
How much would we use the Profiscope?
Yes.
Quite regularly. How much would it be affected by say, a surface saturated dry concrete culvert, for example?
It's not really a consideration, but in any significant way.
Okay.
Right. Radar, again, and look, it's not that radar doesn't work. Radar can work reasonably well as well, but you will start to lose depth penetration on radars, and you definitely would need to adjust your dielectric constant or the values that control the thickness of your radar.
So it's negligible, really.
Yeah, practically. I've seen some cases where people use them underwater, at least as a rough tool, though keeping them waterproofed is a bit of a pain.
Thank you.
So we have a question from Dave C. What ultrasonic kit is required? Can something like an FDR 700 calibrated for concrete work? I'm not familiar with that one. Let me quickly learn. Bear with me a moment. I might finish up a recording to